Okay, so this is lecture 23 in the course. I decided to jump to section 15, which speaks about proving lower bound on kernelization. So this is essentially complexity stuff, and as such the proofs, the proof are complexity proofs, so which turns out, everything is a bit, the proof are you have to be careful about stuff, and things are a bit abstract. And my presentation would be some kind of a random permutation of the presentation in the book, because I think that things are very technical, but somehow it's not easy to understand when you arrive to the interesting points. So what we want to do, we want to prove that there are problems for which you cannot compute a small kernel, right? And the reason, the ultimate reason why we cannot do it is because, for some problem, is because it's essentially, kernels are essentially, if you have a polynomial kernel, you can compress it in polynomial time, right? So, and having a compressor like that is a very powerful property, right? So certain problems have some composition property, which ultimately leads to, if they had a kernel, then we will get something similar to P equal NP. Not quite so strong, but something somewhere, some collapse in the polynomial hierarchy. Okay, so let me start with definition, which is kind of the crux of the matter. Definition 15.8, which is this polynomial compression. Okay, so what is polynomial compression? We have a parameterized language. So a parameterized language, you can think about it as being subset of the strings, times, a natural number, which is the parameter. And we have we have the compression, right? This is a mapping that maps it into a language R, which is part of sigma star, right? And what do we want, right? So the output instance, okay, so we take an instance, I of Q, and we map it by this function f, right? There's the compression scheme. It of course has to be polynomial time scheme, otherwise what's the point? And we want the output string, right, so let me try to write it again. We have an instance ik, and f maps it into a new string. It outputs into a string y, such that, what do we want? Well, we want that y would be short, right? Y has to be length that is polynomial in the parameter k, right? This is really what kernelization means, right? We reduce it to some function of k, and we want it to be polynomial compression. So p is a polynomial. That's important. Okay. And of course, the second property we want, that y is this in this language R, if and only if the input instance is in Q. Right, so that's a compression. Okay, so that's the definition, right? So ultimately, our purpose is to prove that there are problems for which this does not exist, right? And the intuition why for some problems it doesn't exist is because for certain problem, what we have they're composable. So right, and the intuition is that if a problem is composable, then it's, you know, it cannot have a polynomial composition. We're all speaking here about problems that are at least NP-hard. So okay, so let's formally define this composition. So this is definition. Right, so okay, so to see, okay, so what is the definition? So this defines cross composability, which is this very okay, so this is defining cross composability, this definition 15.7, and we say, I should maybe write what it says first. So it says that we can compose, so this is cross composing L into Q. Okay, so the definition of this cross composability is quite long and complicated, so let's go through it. Okay, so what is going on? We're given a language L, and we are given a parameterized language Q. So Q is a language with a parameter, right, a regular thing. And first we need, so there are some technicalities which are not very interesting, but they're kind of important. So we have an equivalence relation on the inputs, right? So the way to think about those equivalent relations, think about, those are polynomial equivalence relations. So this means this is some relations on the input for the problem L that are easily checkable in polynomial time, and they partition the input space of input of size n into a polynomial number of classes, right? So the best example is, you know, think about the input being a graph with n vertices. So you can, for example, compose it into equivalent classes according to the number of edges it has, right? Number of vertices and number of edges. If you know, I give you a graph and I said it has n entities, either vertices or edges, then if I say two instances are equivalent, if they have the same number of vertices and number of edges, then input of length with n entities have defined n square equivalent classes, and we can check if two inputs are equivalent under this relation polynomial time. It's very easy, right? We just count the number of vertices and edges. So we have some relations like that, right? This is really a technicality which we shouldn't care about too much. Okay, so cross composability says we can take a large number of instances, t instances. I wrote n, but this should be t in fact. xt, right? Think about t as being very large, relatively speaking. So we take t instances that are equivalent under this relation, and we have an algorithm. The algorithm runs in polynomial time in the size of all those instances put together, right? And it outputs a new instance y of k, right? And this new instance has certain properties. So first we require that the parameter k is not too large. The parameter k has to be a polynomial size. The polynomial this is critical. The polynomial size is in the maximum size of any of those instances xi plus log t, right? For the time being, just forget about the log t, right? So because log t is very small. So the intuition, although this would turn out to be important later on, but intuitively what happens is that you can take a huge number of instances and map them into one instance, right? With parameter k, and parameter k is going to be small. It's the size determined by the largest instance in your T collection of instances. It's not determined by T, right? If we ignore the log. So, and the important critical property is, of course, that this new instance is in the language Q if and only if there exists one instance that is in the original language, right? Okay, so what really this cross-composability means? This cross-composability intuitively means that you can intuitively, so this is the inverse of compression in some sense. You can take a large number of instances, right? Or if you want it, it's in some sense intuitively, in fact, another type of compression. But intuitively it says, you can take a huge number of instances and generate one instance, and you do it in polynomial time, and this instance has a parameter which is small, such that it's true if and only if the original instances are true. And the intuition is that if you can do this cross-composability, then you're very close to being able to solve the problem in polynomial time, right? That's really what the intuition is, right? Assuming that you can solve the instance yk quickly, right? So, because intuitively what it really means is that I give you a large number of instances, and if one of them is true, you can kind of detect it. You're not quite detecting it, you're just generating this instance that is true if one of them is true. But it's a very strong property, the fact that you can do this composition together, right? Okay, let's see maybe an example of this cross-composability. So a natural example would be the longest path, which of course is an NP-Hard problem, right? So longest path, right? So you're going to give me graphs, G1, G2, Gn, okay? And let's assume that they are all equivalents under my equivalence relationship. So my equivalence relationship here would be the number of vertices is the same, the number of edges is the same, and we are looking for the longest path. The longest path is the same length. Okay, fair enough, right? In fact, in this case, we can maybe in fact take Hamiltonian path and just say, we are taking instances of Hamiltonian paths, right? Okay, so we take all those instances, and now what I'm going to do, I'm going to just generate a graph H, which is going to be just, the graph H is just going to be, I copy those graphs, right? It's going to be a large graph where every one of those graphs is going to have its own copy, right? Okay, and now we can ask, is there a path of length is, this graph is going to be, since I have T graphs, not N, I'm doing this mistake again. There are T graphs, so this input is going to be of size Tn roughly, n is the number of vertices. Is there a graph, is there a path of length k in H? Right, where k of course is n in this case, right? If we are asking for, are there in any of those instances there is a path of length n, right? Because we asked all those instances to be equivalent, for example, the Hamiltonian path thing. So so that's the question, right? And it's clearly it's a composable problem, right? So and the intuition is that if we can compose the problem, right, and in addition now, not that the instance is quite large, right? So we took those instances and we generate a large instance, but the parameter is relatively small. And the reason why the parameter is relatively small is because we can take t to be very, very large, right? So we composed all those instances and got this instance. Now, if we had a polynomial compression, if we had a polynomial kernel for this problem, then we can reduce this problem. You can take this new large instance and reduce it into, a problem of size polynomial in K, right? And that would be very strong, right? And why exactly this is very strong and so on, we need to work further to see that. But that's the intuition, right? The intuition is that if a problem is easily composable and it's hard, then it cannot have a polynomial kernel. If it has a polynomial kernel, that it cannot be composable or cross-composable. So let me give you an example of maybe that, right? Think about things like vertex cover, our favorite problem, right? So I give you n instances of vertex cover, g1 to gn, right? I give you n instances, they're equivalent, right? And intuitively, we don't know how to put those instances together, right? Let's assume that somehow I could try and do the same thing as before, right? And put g1 here, g2 here, to gt as usual, to gt. But then in this new instance, what am I going to ask, right? So I can ask, for example, let's assume that all those problems have the same parameter. They're equivalent with parameter k, right? For all of them I'm asking together, is there a vertex of size k? Then, intuitively what I want to ask is, does this huge graph have vertex cover of size kt, right? I'm saying it in double quote because, of course, this is completely false, right? The fact that there is a vertex cover of this new graph of size kt doesn't tell you anything, is not a sufficient condition, right? Because one of those graphs might have vertex cover larger than k, and all the other would have very small, so the big graph would not have vertex cover of large kt. So vertex cover intuitively is not composable, right? This is not a proof, this is hand waving. I hope you can hear the wind in my voice. But that's the intuition. The intuition is that somehow vertex cover is not composable under this OR operation, right? Although it, of course, has a polynomial kernel, right? And this is kind of what the situation that we are going to encounter, right? If it's a polynomial if there is a polynomial kernel, then the problem is not composable. If it's composable, then there is no polynomial kernel, right? That's what we want to prove. Of course, we need to prove that having this composability together with the polynomial kernel is not good, right? And for that, we need to go back and prove some results in complexity, which is what I'm going to do next. Okay, so we need to start talking about some complexity stuff. And let's start by talking about the class CoNP, right? So CoNP, of course, is the class where if the answer is no, there is a proof, and this proof can be verified in polynomial time, right? It's the complement of NP, where in NP, if the answer is yes, there is a compact proof that can be verified quickly. Okay, and of course, the belief is that we have, right, to remind you, this is NP, this is CoNP, and the belief that they are not, and the intersection, of course, is P, and the belief is, of course, that they are different, and here there is this NP complete or NP hard problem They're somewhere here, right? So that is the belief of the situation. Okay, now we can enlarge CoNP, right, by giving it some extra magical proof, and CoNP poly, right, this is the following class. This is a class where the algorithm is given an advice, together with the input of length n, the algorithm is given an advice string of polynomial length, right? And then the algorithm runs in polynomial time, okay? So the way to think about it is that NP, CoNP over poly is slightly bigger, right? Not dramatically bigger. Okay, so what this class really is CoNP where with non-uniform model, right? For an input n, there is an advice string of polynomial size, which, you get for any input of size n, right? Now, non-uniformity doesn't help you much, but it gets you something. Okay, so what it really means is CoNP poly, because non-uniformity doesn't buy you much, CoNP over poly is a slightly bigger class. It should be slightly bigger than CoNP, right? Slightly bigger, right? But still, we believe that they are not, this is CoNP poly. Okay, so we definitely believe that it's still not equal to NP, and definitely we believe that this is false. Believe, belief is that NP is not equal to CoNP over poly, right? Oops, CoNP over poly. And in particular, we believe that NP is not contained. This is false. It's not contained in CoNP poly. Okay. So if we get that NP is contained in CoNP over poly, then intuitively we got a contradiction. It's a complexity contradiction for what we currently know and believe, but it's not quite as strong P not equal NP, but it's pretty strong as far as we are concerned. Okay, so ultimately, our purpose is to prove that this compression stuff is right. We want to prove that there are no polynomial kernel, and right. And now our purpose was to argue that this cross composability together with polynomial kernel together is impossible. And for that we now need to speak about essentially show that ultimately if we have both property, that would lead to NPs containing this CoNP over poly. Okay, so we need several definitions, and then and also, as I said, are completely complexity stuff. So essentially, the rest of the lecture is going to be about complexity. So we have two languages, L and R, over an alphabet. Essentially, the alphabet, you can think about it as 0, 1. It doesn't really matter. And we are assuming that we have an OR distillation of L into R. So this is similar to this cross composability. We have strings x1 to xt in sigma star, right? And in polynomial time, time, we can compute a string y, such that, and you know what you would expect, such that y is in R if and only if there exists an I such that xi is in L. Right. So this is what we have. So that's the first property. The second property we need is that the length of y is not too long. Right. The length of y, so it's the same stuff we seen before. It's polynomial, but in the maximum of the length of the input string. Right. Right. So the string y is relatively short. And again, what matters here is the length of the the maximum length of the xi's, not the number of xi's. In particular, t here is a free parameter, right? So our distillator is a very strong property because you can take t to be very, very large, right? And effectively what you're doing, you're taking all those t instances and you're compressing them into one instance, such that the instance is true if and only if one of the original instances is true, right? So it's a very strong property. And intuitively, if we have a problem for which we have this or distillator, then it's almost solvable efficiently, right? So it's not quite going to be in NP if we have this property, the language L. It's going to be in slightly higher language. It's going to be in fact in this co-NP over L, co-NP over poly that we saw before, right? Now, to see why this is true, observe that if we could, for example, so think about the ultimate instance. L is polynomially solvable, right? Then we can go for every xi, we can check whether or not they're in L, right? And if one of them in L, we just output some trivial instance in R, which is yes. If they're all no, then we output some trivial instance that is no, right? So in this case, we get it very easily, right? And the intuition is because, so this is ultimately this distillation is really a compression algorithm. And the intuition is that since we can do the compression in polynomial time, the problem is almost solvable in polynomial time. That's the intuition of what's going on. The proof, you know, of course, to prove what I just said formally would require some additional work. Okay. Next stop. Okay, so the claim, that I'm going to prove is the following claim. The claim is that if there is an or distillation between two languages, L and R, then L is co-NP over poly. The amazing thing about this theorem is that the language R, we assume nothing about it. R can be, you know, undecidable even, right? It's kind of pretty amazing, right? It's essentially, what really it says is that having this O compressor really means that the problem is almost efficiently computable. That's the way to interpret it. And the proof, let's start going to it. It's a bit subtle, but it's not too bad. So first I'm going to assume that the alphabet is just 0, 1. Why not? Right, just make things easy. And we have this O compressor algorithm, right? The algorithm that takes those instances x1 to xt and generate this instance y in polynomial time, right? This is the O compressor, the O distillator, dist. Okay. Now the trick, you know, we assume that this algorithm works in polynomial time, right? So this is the running time. This is the running time of A, right? It's a polynomial in the input size. In fact, no, I have to be more careful, sorry. This is not the running time, this is the length of the output. Length of y, right? We assume that the length of y is bounded by some polynomial p of n, right? Where n is this, right? To remind you, n is just the maximum of the xi's, right? So if you look at the definition, right, n here is the maximum length over I going 1 to t, of the length of the xi's, right? So we have a polynomial p of n of that. Okay, now the trick is that we can pick t, the number of strings, to be as large as we want, right? Because it's a free parameter. So we're going to pick it to be very large, right? How large? Well, we're going to take it to be k plus 1. Okay. You know, if you want, you can think about it as pn plus 1. Okay. So we're going now to fix this parameter t, which we are allowed to do. And now what is going on? So we're going to look on all strings, right? Because we have input strings on L, right? We're looking on all the input strings, right? So those are all the input string of length at most n, right? Sigma. Think about it, all binary strings, right? And inside this binary string, we're interested in the subset that belongs to L. This is L, okay? And maybe I should draw L as a bit larger, right? We're interested in this part. This is L, and this part in the middle is going to be sigma n smaller or equal than n intersection with L, which we're going to refer to as A. A are the good strings, right? Essentially, we are trying to come up with an algorithm that would decide whether a string is in A or in the complement of A. Right? This is the complement of A. Okay. That's really what we are trying to do. Okay. But now because we are dealing with t strings, right, t input strings, we're really interested in the set D. D is, let's write it here, D is equivalent to all the inputs to the order distillator, so it's all the string of length n to the power t, right? And again, t we fixed above, it's pretty large, right? So D is this size of this D tuples, and right, okay. And now what is going on, right? What's going on is that we have this set D, right? And we have the algorithm A, right? The algorithm A takes all those strings and map them into these strings of length of length k, right? At most k. Okay. Okay, so that's what this order distillator does, right? It takes a t-tuple, it maps it into this, right? Now, of course, we're not interested in all the tuples in the language, right? So we have the language R, So here's the language R, right? This is R. Oops, maybe I should do it again. We have the language R, and we have the intersection. And the intersection, we are going to refer to it as B. B is R, this part. B is R, intersection with, and of course, as before, we have the complement, which is overline B, which is all of this. Which is all of this, and this is again sigma at most capital K. Okay, so this is what's going on, right? We have set B, we have that. Okay, now now we can think about the good tuples and the bad tuples. So what are the good tuples, right? The good tuples are A, right? So what is A, to remind you? A are all the original strings that belongs to A, right? So think about all the tuples that are made, that are made out of only good strings. In fact, it would be more useful to look on the complement set. So we look on all the bad strings, all the strings that don't belong to L, and we look on all the T tuples of them, right? Those tuples, right, the algorithm A have no choice, right? It has to map them into strings that are not in R, right? So this is mapped into A maps this set into a subset of not B, okay? Okay. By the way, what you hear in the background are real birds, not fake birds. Okay, so now what is going on? What we are going to claim is that this set, right, the bed set, right, right, the bed set, intuitively what we want to claim is that the bed set can be covered by a few strings in B, right? So formally, and this is kind of the crux of the claim. So this is claim 15.5. Oops, let me use a different color. Oops. So claim 15.5. So the claim is that there exists a set Y, which is subset of B, not B to be more precise. So it's here, right? The set is very small, right? The set Y is going to be smaller than n plus 1. Okay? And why is this set interesting? Y covers not A. Okay, so by now you must have forgotten what not A is, because I forgot what it is. So not A, to remind you, are all the string of length at most n that don't belong to the language L, right? Okay, so those are all the bad string, right? They are not in the language. But what does it mean to cover it, right? So here's what it means. It means that x, for x in not A, right, a string that is not in the language, there exist strings x1 to xt minus 1 such that such that a of x and x1 to xt minus 1 is equal to y, right? Now to remind you, y is in not b, right? That's what we said, right? The strings, so x is in not b, right? The set y is in not b. So that means that all those strings x1 to xt minus 1 are all also not in A, right? So essentially what it says is that we have, the set y in some sense for every string that is not in A, right? We have a string in y, which proves it, right? We can guess those other strings, and to A together with those strings would map into the string y, which we know is not in the set, right? So that's really what it means, right? So it essentially says is that we need only a very small number of strings. Going back to here, we need very few number of strings in B, this is the set y, n plus one of them, such that we capture all the strings such, let me, right. We need very few strings in not B such that we capture all the strings intuitively that are in not A, right? It's a bit confusing, but it is what it is. Okay, so that's the claim, and we need to prove the claim. Once we prove the claim, the proof of the theorem is pretty straightforward. And the idea of the proof is that intuitively what we're going to do, the proof is a greedy algorithm. Okay? Okay. So how is the greedy algorithm going to work? The greedy algorithm is going to work as follows. We start, let me S1 be not A. Okay? And now we are going to pick y in not B that covers most strings in S1. Let's call it X1, you know what, just to be consistent. You know what, let me call it Y1, right? We pick the string that covers the most in S1. And now we repeat the process, right? S2 is going to be all the strings that are not covered yet, right? So it's S1 minus A minus 1 of Y1, right? So A to the minus 1 of Y1, you can think about it, all the strings that the string Y covers, right? Okay, so this is the remaining string that remains to be covered. And again, we repeat in the same process, right? We pick the string that, this is not we don't care about running times, right? So this is just a greedy algorithm. We're going to repeat this process, okay? So why is this process working? Well, the idea is that, right, think about it. SI are all the strings that are not covered, right? So the number of strings they define, right, the t tuple they define is SI to the power t, which is a large number, okay? Now, the algorithm A takes all those tuples, SI to the t, and map them, right? What does it map them? It takes a tuple like that and it maps them into the string sigma of k, right? Because that's what we defined the target, right? That was the parameter we picked, right? Okay, and sigma at most k, the size of this sigma at most k, because we assume the alphabet is of size, this is just 2 to the t,
well, it's 2 to the k plus 1, which is really 2 to the t. Okay, so in particular, by just the pigeonhole principle, there must be a string that is in the target that is have a lot of string mapping into it, right? There must be a string that covers. How much does it cover? It covers at least, well, the number of tuples, as we said, is si to the power t, right? This is the number of tuples, divided by the number of output string of a, right? So this is, as we just said, it's 2 to the t, right? So there is a string, there exists string yi plus 1, let's say, that covers at least this number of strings. Right. Now, this is a bit confusing, but if you do the arithmetic, this really means that y covers half the strings. In SI. Okay? And now we are done, right? If this is true, then we are done, right? yi plus 1 covers half the strings. The number of input string is sigma at most n, right? Which the size of this set is 2n plus 1. Every time we run the greedy algorithm, we find a string that covers half of the remaining space. So after n plus 1 iterations, we are done. So that's it, right? So I just need to prove to you that this condition is indeed true, right? So let's prove that. This condition is not hard to prove, just a bit bizarre, but that's okay. Right? Life is a bit bizarre. So let's do it. Okay. So let's look on the string of SI. I think my index is off what's written in the book, but hopefully that's okay. Okay. So SI divided by 2 to the power t, right? This is smaller, right? So, right? So at least this number of strings, right? This is what we just argued before. This is the number of strings that are covered by the string yi plus 1, right? So a to the minus 1 of yi plus 1, intersection with si, right? This is all the strings that the ith string covers, right? So all the tuples, right? So we do it for the power t, right? So ai minus 1 of yi plus 1, to remind you, is a t tuple, right? It's all the t tuples that are mapped to the string yi plus 1. And, you know, we argued that this was at least half the tuples. You know, we argued that the number of these tuples is at least what's written on the left side. So we have this. But this, what is this? Well, this is all the So those are all the tuples lost, right? So this is Si plus 1. This is a bit confusing. This is Si minus Si plus 1, right? Those are all the string that got covered. You know, you look on all the string that got covered in the in this process, right? You know, so so one needs to look at it a bit in this inequality to say what it's true. So let's go through it. So this is all the tuples. What is written here? Here we have all the tuples that got covered by the I plus 1 string, right? All those tuples. And formally, all those tuples that got covered, right, are just well, those are well, all the strings that got covered. This is exactly the set of Si minus Si plus 1 are exactly the string that got covered by Y, right? And if you raise them to the power T, right, those are all the strings that did not get covered, right? They're still not covered afterwards. And you raise them to the power T, those are still the strings that are not being covered, right? Okay. Let's see if I can say it in a more convincing way. Okay, to see why this is true, you need to look on the following bizarre inequality. So let me write it, and then we argue why it's true. A to the minus 1 of yi plus 1, y, intersection with si to the t, right? This is contained in si minus si minus si plus 1, right, to the t, right? Okay, so to see why this is true, observe that right, so this is containment, right? So take a string on the left side. This is a t tuple that was covered. This is a t tuple that was not covered in Si, but it's covered in Si plus 1, right? Because it's covered by this string. And such a tuple does not need to have all of its elements covered, right? It's only one of the elements in the tuple needs to be covered by this new element yi plus 1, right? So okay, so to understand this inequality, we need to look at it a bit, right? So Si minus Si plus 1 are all the strings, that got covered in this iteration, right? And and the important thing is that if you look on Si of t are all the strings that are in this stage are still yet to be covered, right? So if we take all the strings that we cover, you know, the definition of this coverage essentially means that for every tuple that is in ai minus 1 of I plus 1, right, it maps to yi plus 1, right, and it's being covered, right, then this string immediately, defines all those, this string is being covered, and as such, so how to say it in the right way, then those strings are essentially contained in this set, right? Because every string that gets covered, right, by yi immediately takes any tuple that contains it, right? So the only tuples that survive are the tuples that are in this set. And that's why we get this inequality, this red inequality, and applying it to the above, right, says that we give us this inequality, right, the above inequality, right? So this inequality says that si to the t divided by 2 to the t is smaller or equal than si minus si plus 1 divided by t, right? Okay, so let's rearrange. We get si is smaller than si minus si plus 1, right? This is the loss that we get in this iteration times 2, right? So the number of elements we lost in si in this iteration is at least half the set, namely si plus 1 is smaller than si divided by 2. And at this stage we are done, right? Because the number of S0, the size of S0 was at most 2 to the n plus 1, right? So we got that this greedy algorithm takes at most n plus 1 steps, which means that we prove the claim. So this is proof to the claim. There is a small set of strings that cover all the strings. Okay, so we proved this claim. This claim was that there is this small covering set, and we needed it to prove a theorem. Remember, we were trying to prove a theorem, which of course by now you completely forgot what the theorem about. So let's go back and restate the theorem. Right? The theorem was that if we have two languages L and R, and we have this OR distillation from L to R, then L is contained in coNP over poly, right? And then we have this, right? And this OR distillation was all about this T, that we have a polynomial time algorithm A that take T tuples of strings and essentially compress them into this one instance, which is true if and only if the original instance is true. And the trick was to pick, we took a string of length n, and we picked t to be sufficiently large such that the number of tuples was huge. And then we argued that, we looked at the algorithm A, it ultimately mapped all the strings of length n. If we looked on the t tuple, this is the space D, it mapped them into this strings of length at most k, right? So it performed compression essentially. And we argued that because of the way we picked t to be sufficiently large, this corollary held, right? There was a few number of strings here such that every bed tuple, right? By bed tuple, I mean a tuple where all the strings in the tuple did not belong to L, got mapped into those strings, into the one of the bed string here, right? So now how this is related to coNP over poly, right? Our advice string is going to be the set Y, the set of n plus 1 strings that covers this complement A to the T, right? we're going to just list them. So those are n+1 strings, and k, to remind you, is a polynomial in n. So the encoding all those n+1 strings, this is going to be polynomial in n, right? So we have this advice string, which is polynomial length, and the algorithm gets it. It's a non-uniform string, right? And now you give me a string. You give me a string in A. Sorry, you give me a string in this space of input, right? Sigma, a string of length n. And here's what I'm going to do. We allowed polynomial time non-determinism, right? So we're going to look on this t tuple. T is polynomial, right? So we're going to guess all the strings except for this string, right? We're going to guess all the strings except for this string. And then what is going to happen is that we're going to, take all the strings that we guess together with the input string and apply the algorithm A to it. The algorithm A is polynomial time, so we get a string. In sigma, with at most k characters, and now we can check whether this string, right, whether the string belongs to one of those n+1 strings that are covering the bed space, right? So this we can do, right? So ultimately what we got is that if we can do this, if we have all this tiltation, then we can, if the word is not in the language, we have, we can decide it in this coin P over poly, right? Because we needed the advice, which was the set Y, the covering set Y. This is where the poly came in. We needed the instance to be a no, right? That's why the co-part is there. And then in non-deterministic time, which we guessed all these other t-1 string we needed, which we did polynomial time, this where we had this NP part. We guessed all the strings, we in polynomial time computed, and then we just compared if this string appeared in the advice string. So we got the result, right? We got that the language L is coin P over poly, right? A string being in this set is this bizarre thing where you're not recognizing the language, you're recognizing the complement language, right? But that's fine, that's legal. Okay, so we got this theorem. Why does it help us in life? That's a very good question. Okay, so the implication of the theorem is the following corollary, which is relatively easy. And what this corollary says is that if we have a language which is NP-Hard and it have an O distillation, then immediately we get that NP is contained in this coin P over poly, which we believe, as I said earlier, to be false. And the proof is, of course, immediate. Well, take any problem in NP. So we have NP. Pick your favorite problem, L. Well, L is not a good choice. Let's call it L prime. We pick any problem L prime, right? Now, because L is NP-Hard, there is a polynomial reduction. Poly reduction. Okay? There is a poly reduction into L. Right? That's what it means that L is NP-Hard. Now, by the O distillation, right, L, we know that L is in coin P over poly. Right, that's exactly what we proved, right? But this is the theorem, right? But that immediately implies that L prime is in coin P over poly. End of proof. Right. Okay, so And again, there is this really bizarre thing here where the order distillation is to this language. We don't even have to be decidable, which is really kind of bizarre, right? It really says being able to do this bizarre compression is extremely unlikely. Okay, so now we want to go back to the parameterized complexity stuff. Okay, so what we have is this theorem 15.9, which again we have L is an NP-Hard problems. And we are assuming that it cross composes into a parameterized language, into a parameterized language Q, right? So if this happens, then there is no polynomial kernel well, polynomial kernel, to be more precise, polynomial compression. This is kind of not quite formally true. Polynomial compression, unless pigs can fly, unless NP is contained in co-NP over poly. Right, and you know the proof is going to essentially be plugging this stuff into this complexity stuff we saw, right? There's all this tiltation and so on. Namely, what we're going to show that if there is this polynomial compression, right? Essentially, we have intuitively think about it as a polynomial kernel. Then what happened is that we can get an OR distillator for the language L. And this in turn implies that this NP is contained in co-NP over poly. And the proof is not very difficult, but it kind of uses everything we've seen so far. And I think you probably have a brain overload. I have at least have a brain overload. So let's declare victory, because I studied the theorem and hopefully kind of have an intuition why it holds. And we draw and end the lecture here. Thank you very much.